All right, so section 2.2, solving inequalities by adding or subtracting. So just like inequality, when we solve an inequality, that means we want to isolate the variable, as always. So you want the variable on one side, the inequality symbol, and then the number. So that's going to be our format. Let's go over some properties of inequality. Hang on a second. I keep pressing the eraser by accident. All right, so the first property we're going to have is addition. Oh my God. There we go. The addition property says that you can add the same number to both sides of an inequality and the statement will still be true. Just like when we had equalities and we would add something to both sides, what you do to one side, you must do to the other. The same applies to inequalities. All right, so you can add the same number to both sides of an inequality and the statement will still be true. For example, say we have 3 less than 8. That's true, right? 3 is in fact less than 8. So let's say I add 2 to both sides. Plus 2, plus 2. 3 plus 2 is going to be 5, and 8 plus 2 is going to be, I'm sorry, not 6. What am I thinking? 8 plus 2 is going to be 10. And we keep that inequality sign. In other words, we have 3 less than 8. I'm going to add 2 to both sides. So 3 plus 2 less than 8 plus 2. Then we get, for that, we get 5, 10, and we're just going to bring that guy down exactly. And 5 is still less than 10. So yes, this is correct. So to write that in more general terms, if we have A less than B, then A plus C is still less than B plus C. All right? So what you do to one side, you must do to the other, and it maintains the inequality symbol. All right, now let's talk about the subtraction property. So just like the addition property, the subtraction property states that you can subtract the same number from both sides of an inequality and the statement will still be true. So, for example, we have 9 less than 12. That's a true statement. 9 is less than 12. Now, say I want to subtract 5 from both sides. So I have 9 minus 5. Why did we switch colors? Nine minus 5 less than 12 minus 5. See how we're subtracting that minus 5 from both sides? Well, 9 minus 5 is going to be 4. 12 minus 5 is going to be 7. And we bring this guy down, and 4 is still, in fact, less than 7. So, again, you subtract the same number or add the same number to both sides, you maintain that symbol. That symbol doesn't have to change. So let's put that in more generic terms. We have A less than B. Then A minus C is still less than B minus C. All right, now the subtraction and addition properties are also true for the other symbols as well. So subtraction and addition properties, whoa, okay. Are true for all the inequality symbols. So less than, greater than, less than or equal to, greater than or equal to. Any of these, it's still the same property. If you add or subtract the same number from both sides, they stay the same. The little alligator is still eating the correct one. All right, now we're going to use these properties to solve inequalities. So for example, say we have x plus 9 less than 15. We're going to use the subtraction property. So just like we wanted before, to solve this, we want to isolate the x. And who's hanging out with x? 9. How would we get rid of 9 in a regular equality? We would subtract from both sides, right? Well, that still holds true for this. So we do minus 9 over here and minus 9 over here. Plus 9 and minus 9 are going to cancel. We have x on that side. And then we have 15 minus 9, which is 6. So our x is isolated. So we are done. All right, let's graph our answer. So we have our key term, that is 6. Let's do some to the right. So we're going to have 7, 8, some to the left, 5, 4. All right. So we have less than. So is that going to be an open circle or a filled in circle? It's going to be an open circle. It does not include the 6. It is very sad and empty. No 6 in there. And we want all the x's that are less than 6. So all the numbers less than 6 could be our x, like this one, any numbers over here. So all the numbers to the left of 6. And that is the graph of our solution. All right, let's do another example. So we have d minus 3 greater than negative 6. So we want to solve this, which means we want to isolate the d. This guy right there. All right, and if we had a regular equality, what would we do? We would get rid of that 3, right? That negative 3, and we get rid of that by adding. So we add 3 on both sides, because even with inequalities, what you do to one side, you must do to the other. So these two are going to cancel. We have d greater than, and then negative 6 plus 3 is going to be a negative 3. And that is our answer. Now let's go ahead and graph that. So negative 3, negative 2, negative 1, negative 4, negative 5. All right, we don't have a little line down there, so that means it's not or equal to. So does that mean it includes the negative 3 or not? It does not. So is that going to be a filled in circle or an open circle? An open circle, it's empty. It doesn't have the negative 3 in there. All right, and we want all the d's that are bigger than negative 3. So all the numbers that are bigger than negative 3 are going to be on this side of the timeline. And if you don't know, just ask yourself, is negative 2 bigger than negative 3? Yes? Okay then. Point our arrow in the direction that the negative 2 is. And that is our solution. All right, another example. 0.7 greater than or equal to n minus 0.4. All right, remember, we're just going to pretend it's an equality just for the time being. And we're going to move stuff around just like we would in an equality. We want to isolate the n. And who is hanging out with n? That negative 0.4. And how do we get rid of it? Adding 0.4 to both sides. So those are going to cancel. We have 0.7 plus 0.4, which is going to be 1.1. Keep that. Just bring it on down. And don't forget the n on the other side. So now n is by himself. And we have n and the number and the inequality sign. So we are done there. Let's go ahead and graph that. Now, if you want, you could flip this around so that n is first. If not, you can just deal with it like this. So we have 1.1, and let's see, I'll just put 2 over here and 1 over here. Totally not to scale, but that's okay. So we have a greater than or equal to. So does that mean our circle is going to be open or closed? It's going to be closed. It includes that 1.1. Our little bag is full. Now we want all the n's. So is n going to be bigger than or smaller than 1.1? The little alligator is eating the 1.1, so that means the 1.1 is the bigger one. And n has to be the smaller one because the alligator doesn't want to eat it. The alligator wants to eat more. So we want all the numbers that are smaller than 1.1. Is 1 smaller than 1.1? It is. So we're going to draw our arrow in that direction. And that is our graphed solution. And if you want to flip this around, you totally can just from there by looking at it. Going n less than or greater than 1.1. Or you can do it from here too, in which you know that all the possible n's over here are less than or equal to 1.1. Whichever way, doesn't matter. But this is the proper way to write it with the variable first. All right, so when we have an inequality, I don't like decimals, so we're not going to use that one. Let's say n less than 1. So a little circle there, 1. Let's do less than or equal to 1. Why not? 0 and 2. All right, so obviously there's infinite numbers that are less than 1, right? That goes on and on and on forever. Is my pen working? No. All right, so it is impossible for us to check every single solution. So what we do is we check the endpoint and then a solution inside the given range. For example. All right, so what do I mean by the endpoint? I mean this guy, our key number. And what do I mean by a number in the range? A number in this area where our arrow is pointing. So for example, we would try 1. And with our key point, we're going to try equal to. So we're going to have n is equal to 1, and then n less than or equal to 0, and up. All right, this is just so you can get an idea. This isn't exactly what we're going to be doing, obviously. So let's go ahead and solve an equation. So for example, we have x plus 9 less than 15. Now, to solve it, remember we did x, well, we'll just do it again, it's fine. So minus 9, those cancel. X is less than 6. All right, and we had it graphed, looked like this, with an empty ball in the 6. All right, and then all the x's that are less than 6, so this way. So, step 1, we're going to check the endpoint. Now, when we check the endpoint, remember that sometimes it includes that number, sometimes it doesn't. When we're checking, we're going to say that it does. So we're going to do x plus 9 equals 15, and we're going to let x equal 6. So 6 plus 9 equals 15. So 15 equals 15. That is correct. So we want that endpoint to be a solution to the equals version, right? Because that's where it starts. Now for step 2, we're going to check for a number in the range. So we're going to check the inequality symbol. All right, so what does that mean? That means I'm going to pick a number less than 6. So let's say 4. We're going to pick a number where that arrow is going to make sure we're right. Well, let's move this up a little bit. We're going to let x equal 4. So here we're checking the inequality. So we're not going to do an equal sign. We're going to do the original inequality that they gave us, which is a less than. So we're going to substitute 4 for x. And we get 4 plus 9 is less than 15. Well, 4 plus 9 is going to be 13. 15 and less than. Is 13 less than 15? Yep. So we are right. And that is how we check an inequality. Remember, we check our endpoint equality, and then we check our inequality with a number not in the endpoint, where the range is of your solutions. All right, so we have this problem that says the memory in Tanea's camera phone allows her to take up to 20 pictures. Yes, guys, this was a reality back in the day. Tanea has already taken 16 pictures. Write, solve, and graph an inequality to show how many more pictures Tanea could take. Ignore all those typos in there. I'm not going to fix them. Moving on. So, her camera phone allows her to take up to 20 pictures. Does that mean she can take 21 pictures? Does that mean she can take 36 pictures? What about 19? What about 20? Yeah, because up to 20. So she can take up to 20. So anything 20 and below. So we'll have pictures be P. And we'll do that P has to be less than or equal to 20. And if that confuses you, you can always draw it. So we have 20, 21, 19. She can take up to 20 pictures, so she can take 19. Good. She can take 20 because she can take up to 20. She cannot take 21. So that means our answer, it includes the 20, which is our key value. So we're going to do a filled in circle, and then we're going to draw our arrow in the direction of the numbers that fit. So 19 fits, so we'll draw it to the left. All right, so P less than or equal to 20. All right, what other information do we have? She's already taken 16 pictures. All right, so she's taken 16 pics already. So they want us to write, solve, and graph an inequality to show how many more pictures she could take. All right, so we have 16 plus P, and remember we can't take more than 20 pictures. So the pictures that she has already, plus however many more she's going to take, has to be less than or equal to 20. Well, let's go ahead and find out what are our possible values of P. So remember, to solve this, we have to isolate our variable. So we're going to do minus 16, minus 16. P, just carry this on down. 20 minus 16 is going to be 4. So she can take less than or equal to 4 pictures. She can take 1, 2, 3, 4, or 0 pictures. That's it. So let's go ahead and graph our solution. So 4 is our key number. I'm going to circle it so we know. Actually, let's not circle it. Let's underline it. And then draw some numbers on this side. Draw some numbers on this side. All right, so we have P is less than or equal to 4. So is that going to be an open circle or a closed one? It's going to be a closed circle because we are including that 4. All right, so our little bag is full because the 4 is in there. All right, now we want all the P's that are less than 4. So is 2 less than 4? Is 3 less than 4? So those work. Is 5 less than 4? No. Is 6 less than 4? No. So our arrow can only point this way. And that is the graph of our solution. Now, last part, we are going to check our answer. So remember, to check our answer, step 1, we check the equality with our key point. So we're going to have 16 plus P equal to 20. We have our key point, which is 4. So 16 plus 4 equals 20. And 16 plus 4 is 20, and 20 is equal to 20, so that is good. All right, success. Now step 2, check the inequality. So we write down our original problem. So 16 plus P less than or equal to 20. And we're going to pick a number somewhere in here. So let's say 3. So P is equal to 3. We're going to have 16 plus 3 less than or equal to 20, which is 19 less than or equal to 20. Is 19 less than or equal to 20? Sure is. So that is a true statement. Therefore, our answer is correct. We have checked our answer. All right, one more word problem, and then we will do our classwork. All right, so we have that Josh can best can bench press 220 pounds. He wants to bench press at least 250 pounds, right? And solve an inequality to determine how many more pounds he has to lift to reach his goal. All right, so he can currently bench 220. His goal is at least 250 pounds. So goal at least 250. So does that mean he wants to bench 260? Yeah, he wants at least 250. So that means that 250 is the smallest. Now, again, if you're confused, just graph it. So 250 at the least. So 250 is our main point here. We'll put 300 over here and 200 here. So at least, that means that this is the smallest number. And it includes that one, right? At least. And all the other pounds that he wants to bench press are on this side. They are more than 250. All right. So we got that. We know how to write our inequality symbol. So we've got 220 are the pounds he can lift, plus however more additional pounds. And then 250 is our goal. 250 is at least. So judging from this little graph right here, we want the number he can bench to be greater than or equal to 250. Let me repeat that. He wants to bench at least 250 pounds. So that's going to be what he currently benches, plus anything that he's going to bench in the future, any pounds he adds on. And he wants that to be more than 250. So he wants the least amount that he could possibly bench to be 250. That's the smallest. That's his weakling status. And then anything more than that is bueno. All right, so now let's solve this. So we're going to subtract 220 on this side, subtract 220 on this side. Write down the P, carry down the inequality symbol, and have a 30. All right, so in order to reach his goal, he has to lift at least 30 pounds. So 30 pounds or anything over. And let's go ahead and graph that. I don't think it wants us to, but let's do it anyway. So let's graph our solution set. So we have 30, 35, and 25. Here's 30. This is an or equal to, so it's going to be a filled in circle because the 30 is in our little bag. It's not empty. And we want all the p's that are bigger than 30. So is 35 bigger than 30? Yeah, so it could be a p. Is 25 bigger than 30? No, so it can't be a p. So we draw our little arrow in the direction of our check marks. All right, awesome. Now let's check to see if we're right. So the first thing we're going to do, step 1, we're going to check that equality. Check equality or endpoint, I should say. So we're going to set up 220 plus P equal to 250. And we're going to let P equal 30. So we have 220 plus 30 is equal to 250. And 220 plus 30 is going to be 250. And 250 does in fact equal 250. All right. That is success. Now step 2, check the inequality. And this is where we write our problem exactly as we had it. All right, and we're going to pick a number in this little area over here. I'm going to pick 40 because I don't want to deal with the 5. So we're going to let p equals 40. So we have 220 plus 40 greater than or equal to 250. 220 plus 40 is 260. And 260, is that greater than or equal to 250? Yes, it is. So the inequality is true. And we are done. We have checked our answer. We are good. All right, are we ready to do some problems on our own? Too bad, we're doing them anyway.